In this video, we're going to talk about Lewis acids and bases and the complex ions that can be formed from those. So back in the first semester of this course, we talk about acids and bases, and we talk about the Bronsted-Lowry definition and the Arrhenius definition. And we pointed out that the problem with the Arrhenius definition is that it defines bases as having hydroxide, but we have things like ammonia that are bases but don't have a hydroxide ion to contribute. So the Bronsted-Lowry definition defined acids as proton donors and bases as proton acceptors. Well, another way that we can define acids and bases is the Lewis definition. So the Lewis definition focuses on electrons rather than protons. So a Lewis acid is defined as something that accepts electrons, and a Lewis base is defined as something that donates electrons. And specifically, we accept or donate a lone pair. So it's always going to be one pair of electrons that gets accepted or donated. So Lewis acid would accept a lone pair of electrons, and a base, Lewis base, would donate a lone pair of electrons. So those of you who are planning on going on and taking organic chemistry will get very familiar with Lewis acids and bases when you go on to organic chemistry. So if we look at an example here, we have ammonia and water. So ammonia donates its pair of electrons to water. So according to the Lewis definition, the ammonia is donating its electrons, so it would be a Lewis base, and the water accepts the electrons, so the water would be the Lewis acid here. So if we look at the definitions of bases, if we look at the Lewis definition and the Bronsted-Lowry definition, a lot of things that can be a Bronsted-Lowry base can also be a Lewis base. So for a species to be able to accept a proton, which is the Bronsted-Lowry definition, it also has to have something that has a lone pair of electrons. So for example, if we have something like ammonia, which is on our last slide, if we put ammonia in water, we know that we get NH4 positive and OH negative. So if we look at this from the point of view of the Bronsted-Lowry definition, ammonia is accepting a proton from water, which would make it a Bronsted-Lowry base. But ammonia also has a lone pair of electrons, which it can donate to water, which would make it a Lewis base. So a lot of species, if they are a Bronsted-Lowry base, they will also be a Lewis base. Sometimes we can have things that would not necessarily be a Bronsted-Lowry base, but can be a Lewis base. So for example, if you have something like F negative, it has a lone pair of electrons, or OH negative, it has a lone pair of electrons on the water. So there might be some cases where those are acting as Bronsted-Lowry bases, but if they're not accepting a proton, they would not be defined as Bronsted-Lowry bases, but they might still be acting as Lewis bases. But you will find a lot of overlap between the two of those. So something like a proton would be a Bronsted-Lowry acid because it's a proton donor. In fact, it is the proton that's being donated. And it would also be a Lewis acid because it can accept a pair of electrons. But there are a lot of cases of Lewis acids that are not also Bronsted-Lowry acids. So, for example, things like cations, so things like sodium or lithium or potassium would not be Bronsted-Lowry acids if they're not accepting a proton, but if they're accepting a pair of electrons from something else, they would be a Lewis acid. Also, things that are electron deficient, so things like NH4 positive, if it were involved in a reaction where it's not taking another proton, in fact, it would not be taking another proton, but it could bond with something else that donates its electrons and act as a Lewis acid. So, for example, if I have something like, and I take something else like, so chlorine has its pairs of electrons, and it can take one of the pairs of electrons and donate it to the ammonium, and we get NH4Cl. So in this example, the ammonium would be acting as a Lewis acid, but it would not be a Bronsted-Lowry acid because it doesn't take a proton from chlorine. And the chlorine would be the Bronsted-Lowry base. So this way of looking at acids and bases expands the number of things that we can see as acids. And this behavior can be used to explain a lot of reactions, especially when we get further into chemistry. So sometimes we can have a situation where we're giving up electrons, but all of the electrons in a bond comes from one particular species in the reaction. So for example, if we have something like water reacting with a proton to form H3O+, both of the electrons in that bond that forms comes from the water, because the proton doesn't have any that it can donate. So when we have a bond like that, where the bond is formed from both, where the electrons are both coming from the same atom, we call that a coordinate covalent bond, or sometimes we call it a dative bond. So this bond that forms between water and this proton would be a coordinate covalent bond. The same thing happens with ammonia when we form the ammonium ion. So we get a bond there where both of the electrons came from the ammonia. So these would be examples of coordinate covalent bonds or dative bonds. So sometimes we get this situation where we have these coordinate covalent bonds. And when we do that, one of the species is a Lewis base and the other one is a Lewis acid. So we call that a Lewis acid base adduct. So for example, if we have fluorine here, which is acting as the Lewis base, it's going to donate a pair of electrons to BF3 to form BF4 negative. Boron doesn't have a lone pair on it to donate. So the bond here has to come from these electrons that fluorine donates. So this new bond between the fourth fluorine and the boron is a coordinate covalent bond. And because we form this bond from a Lewis base and a Lewis acid, the fluorine gives up the electrons and the BF3 accepts the electrons. We call this a Lewis acid base adduct. So another example would be if we have ammonia and silver. So we actually have to have two ammonias. So each one of them donates a pair of electrons to form these bonds that go between the ammonia and the silver. So ammonia is Lewis base, it donates a pair of electrons. Silver is Lewis acid, it accepts a pair of electrons. And we get this Lewis acid base adduct where we have two coordinate covalent bonds formed between the ammonia and the silver. So a lot of these Lewis acid base adducts are complex ions. They're usually polyatomic ions where we have a central atom that's usually a transition metal, and then it's surrounded by ions. And we call these ions or these molecules ligands. So we have two ligands here that are attached to the silver. And this is also a ligand. So we saw on the last slide that these two acted as Lewis bases. And the silver acted as a Lewis acid. So typically the charge of the complex ion would be the sum of the charges of the ligands and the central atom. So if we go back to this example, the ammonia, before we formed this complex, had a neutral charge on it. And silver had a positive charge. The charge on the entire complex is a positive charge. So we can't predict the formula of these complex ions. We can only determine them by experiment. So the central atom bonds that we just showed are coordinate covalent bonds. So these bonds between the ammonia and the silver are coordinate covalent bonds. They came from the electrons that were on the ammonia. Sometimes we call these complex ions coordination complexes. So you'll hear that term, coordination complex, referring to something that where we use a Lewis acid and a Lewis base to form a complex ion. So for example, if we have something like the cyanide ion and the copper ion, so we have our cyanide ion, which has we'll just show the lone pair here on nitrogen. And we have our copper ion. So each of these cyanide ions has a negative charge on it. So each one is going to act as a Lewis base and donate a pair of electrons to copper. So we would get a positive and a negative is 0, but then we have this negative charge here. So that gives us a total of 1 negative on our complex ion. So if we look at the equilibrium constant for that to happen, so remember the way we write equilibrium constants is products over reactants. So that would be over copper we call this equilibrium constant a formation constant. So anytime we have a reaction, there's almost always an equilibrium constant that can be associated with it. So the formation of a complex ion, we call that a formation constant. Those values are typically very large, so we tend to favor the ion rather than the individual components. The inverse of the formation constant is known as the dissociation constant. So if we went in reverse and we hit the copper cyanide, break down into its copper ions and cyanide ions. So the formation of a copper cyanide complex ion is the formation constant. The reverse of that is the dissociation constant. Now, sometimes when we do these processes, we have more than one equilibrium going on at a time. So a few examples of that, and we're going to show some examples on the next few slides. So if you dissolve an ionic solid with a strong acid, and we're going to look specifically at an example of that. Or if we dissolve something that's not very soluble by forming a complex ion. So there's a couple of ways that we can deal with things that are sparingly soluble. And we talked a little bit about this in an earlier chapter. Sometimes we can use a strong acid if we have something that would be more soluble in acid. So something like a basic anion or ammonia, if those are in the compound, we can use a strong acid and help to dissolve whatever our compound is. Sometimes if we have a metal cation, we can add a Lewis base which functions as a ligand, and we can form a complex ion. So let's look at a couple of these cases here. For example, if we take something that's a strong acid, we know that strong acids produce H3O+. So if we have something like an anion or an H3 that will react with the H3O+, we can increase the solubility. So anything that has a hydroxide ion or an ammonia or an anion that's a weak base, we can use the H3O+ to help dissolve those. For example, if we have something like zinc hydroxide. So if we dissolve zinc hydroxide in a solution, we would get zinc 2 positive and 2 hydroxide ions out of it. And then if we have water, we know that there's a very small equilibrium where we get some H plus and some OH negative ions out of that. Well, if we add some acid to this and can react with this OH negative, then we can form water out of that. So what would happen is we would have, so this would technically be H3O+, but we'll just write it as H plus here. We have zinc hydroxide and we have the 2H plus ions in solution. So if we add these together, the 2 hydroxides cancel out and we're left with zinc and water. So essentially what happens is these 2 H plus ions react with those hydroxide ions and we form water, so then we're left with the zinc ion floating around the solution. So we can describe this in terms of Le Chatelier's principle. If we protonate the OH negative with the H3O plus ion and form water, then we're essentially taking this OH here out of solution. So that's what happens in the next step, is this OH negative gets taken out of solution with the proton. So if we're taking this OH negative out of solution, we're going to drive the equilibrium in the other direction to replenish the hydroxide ion as we take it out of solution. So remember Le Chatelier's principle, if we remove a product, we're going to force the equilibrium towards that side. So if we look at this in another way, if we didn't use acid and we instead used a base, well, we have zinc hydroxide, we get zinc and we get 2 hydroxide ions out. But if we have ammonia in there, the zinc can react with the ammonia and form a complex ion where we have a zinc-ammonia complex here. So essentially, we're taking the zinc out of solution, which means we're going to force the equilibrium this way to make more zinc to react with the ammonia. So, just like with the addition of a strong acid, we have multiple things going on in solution. There's a Ksp value for the formation of the ions from the zinc hydroxide. So this is what we talked about earlier in the chapter. And then there's also a formation constant for this complex. So we have multiple equilibria going on here in the solution. So we will get some practice with this and look at some activities where we'll look at some of these situations and talk a little bit more about Lewis acids and bases in class. So I will see you in class.